finite element models. So if everything is good, why do we need to switch to pins? The first reason is that providing labeled data is expensive. Actually, that was the reason we tried to use synthetic motion instead of expensive earthquake data. And that was the reason we tried to use short duration synthetic motions or white noises. The second reason is that the LSTM model or data-driven model suffers from the lack of physical meaning. For instance, in all of our predictions, we notice that there is a small jump at the beginning of all the predictions. It means that the model cannot understand the system is initially at rest and the displacement and the velocity at time zero should be zero. The third reason, which also comes from the lack of physical meaning, is that we cannot do post-processing. And we saw that for a simple operation of subtracting these two corner displacement, the results were bad. So let's start the second project. We considered the pins, physics-informed neural networks, and we considered a 1D soil column, and we wanted to model the 1D wave propagation in this soil column. In this project, we had three contributions. The first one was adding damping term into our governing equations by considering Kelvin-Voigt equation. The second contribution was that we presented a dimensionless format of the equations. And the third contribution was that we wanted to predict the long duration earthquake motions. So let's see how the pin is working. We can generate a bunch of collocation points for our space and time within the domain and also our boundary conditions. Then we can feed the information of these collocation points as the input to our deep neural network and get some output. Then we can use the automatic differentiation to compute the derivative of this output with respect to the inputs we have, and we can compute the latent information. These latent information are velocity, acceleration, and stresses. Then we can plug these latent information into our governing equations and compute the losses. So we have one partial differential equation and a bunch of constraints or boundary condition or initial conditions. And the total loss is the summation of all these loss terms. But because these constraints have different magnitudes, we can assign a weight to each of these loss terms to balance them. In this project, we compared the performance of three different versions of the pin. The first version is the vanilla pin, which all the weights in that version are equal to 1. The second version is the pin that is using ALR as a self-adaptive weighting method and also is using multi-scale Fourier feature for tackling responses with high frequencies. And the third version is our proposed dimensionless equations. So the dimensionless equations are inspired by the normalization technique we typically use when we are dealing with data-driven models. In that technique, when we have labeled data, we normalize them in order to be sure that they are within the range of -1 to +1. But in pins, we don't have access to output. So what we can do is to get the information we have and use the information we have for the boundary conditions and get a rough estimation of what is the order or the magnitude of the output of the network. And after that, we can decompose all the parameters we have into two parts. The first part, which is shown by the asterisk notation, is the part that has the magnitude of that parameter. The second part, which is shown by the bar notation, is the part which is normalized and or is going to be used in the dimensionless equations. And it should be within the range of -1 to +1. So we started checking considering a toy problem. In this problem, the length of the soil column is 1 meter, the density is 1. This figure shows the damping ratio as a function of frequency and the load which is applied at the top of the soil column as the MVC. And here we are showing the finite element responses of this problem. Now we want to see what is the performance of these three versions of the pins that I explained earlier. The first version, which is vanilla pin shown by pin M1, as we see, the predictions are very bad and the errors are more than 100%. The second pin, which was equipped with ALR and multi-scale Fourier feature, performs much better, but still the errors are 40% by considering 20,000 iterations. I should mention that if we increase the number of iterations, this error will definitely decrease, but by considering the same number of iterations, our proposed dimensionless pin can predict the responses with less than 7% error. One of the purposes of proposing dimensionless pin was that it should be able to solve any problem, regardless of what is the mechanical properties and what is the size of the domain. So we switched the problem to a real problem. The length of the soil column is 25 meters, the density is 1500. Again, we have the damping ratio as a function of frequency. And as we see, the finite element response are very similar to the previous toy problem. Although the responses are very similar to the previous problem, we see that pin M2 is not able to provide us with good responses anymore. And the errors are more than 100%. However, our dimensionless pin is still predicting the responses with less than 7% error, similar to the previous case. As the next problem, we considered a soil column where the waves are coming from the elastic bedrock. And for the bedrock, we considered three different cases where its shear wave velocity is either equal or twice or 4 times larger than the shear wave velocity of the soil. And as we say, as this ratio increases, the waves would be trapped into our soil column. But in all cases, the errors are less than 8%, which shows the promising performance of the dimensionless pin. As the final example of this section, we considered a soil column with 2 layers, and we have discrete changes in the mechanical properties of these 2 layers. Because we have this discrete change, we need to do the domain decomposition. In domain decomposition, we assign one network to each of these subdomains, and we can relate the responses of these 2 networks to each other by considering the continuity of the displacement and stresses at the intersection of these 2 subdomains. As I mentioned earlier, we are interested in predicting the seismic responses of long duration earthquakes. For that purpose, we divide the long duration earthquake we have into smaller segments, and we start training our model for the first segment. After the model is trained for the first segment, we can use the idea of transfer learning and pass the information we have and the parameters we have to the second segment. However, we should be careful that the initial condition of this segment are actually the predicted responses at the end of the previous segment. And we can continue this transfer learning till we reach to the end of our grand motion. So in here, we are plotting the loss curves we have for one of the earthquakes. As we see, for the first segment, I considered 30,000 iterations. But as we go to the next segment, I considered only half of the iterations I used for the first segment. And thanks to the transfer learning, we see immediate drop in the losses we had. And these are the loss curves for the second earthquakes. And now we can compare the responses of the pin versus finite element model for the first earthquake. As we see, the errors are less than 7%. And we can plot the responses we have at the top of the soil column, the displacement, the velocity, and the acceleration. The displacement is the direct output of the network, but the velocity and acceleration are the latent information which can be computed in our PIN framework. And these are the results for the second earthquake. As we see in the second earthquake, the errors are similar to the first earthquake, and it's less than 5%. Now we can plot the response spectra for the acceleration we computed at the top of the soil column. As we see, the displacement and velocities are good, acceptable, but we have some discrepancies in higher frequencies for the acceleration spectra.